Hello, this is Team 31 of Avengineers. My name is Frank Lee.
My name is Sarah Kolnicki.
I'm Max Rajana Saktakun.
And I'm Jumbo Chen.
So what's the problem? Due to the sensitivity of semiconductors, even the slightest defects in human contaminants such as hair and dust can inhibit functionality. The elemental contaminant we will be working to combat is electrostatic discharges. Even the smallest voltage charges can build up wear and tear in the circuit, which cost the industry hundreds of millions of dollars. These charges can present dangers to worker safety within higher voltage circuits. Our proposed solution is a wearable and portable system that will be integrated into cleanroom suits. Our device measures the voltage across the user's body to represent the largest electric potential of the person relative to the ground. If it ever surpasses a critical threshold that can damage semiconductors, then the user is alerted of the potential ESD hazard and can simply exit the area and discharge outside of the cleanroom. After consulting a master's student, Lithik, with experience in the field of cleanroom electronics, we found that microchips are often damaged. Although there are existing measures in place like specialized discharging floor panels and tools, our product serves as a failsafe for unintended accumulation of charges due to lack of good practices or understanding in all sorts of facilities and environments. For example, with even seemingly trivial factors like dry skin, electricity may not conduct well, and there can be a charge in the body even with proper grounding. And now we'll give a quick explanation of our system with a video.
So here's a quick overview of our setup. First, we begin at the ESP32 board, which is connected to a Windows machine via micro USB. Then the power output of the board at about 3 volts passes to the capacitors on the separate breadboard, which would allow us to charge or discharge them over a period of time. And the resistor is there to create a more asymptotic and progressive increase with the voltage curve for basically legibility of our data, because we found that when we remove the resistor, the voltage readings of the capacitors almost instantly rose to their capacity, which is not very effective for what we are trying to portray. And our team leveraged the ability of capacitors to temporarily store electrical energy by distributing charged particles on generally 2 plates to create a potential difference. And this is also like the reason why the LEDs indicate like a gradual discharge and charging, like eventually it goes from red, yellow to green or vice versa. And in this case, the quick electric buildup is supplemented by a laptop instead of static electricity over time. And to discharge the system, first we have the warning system in case in this case is the LEDs, and it gives the user a simple and accurate idea of the current status of the device. And it also allows us to demonstrate quickly what might happen over a few hours. And during the actual implementation, we might tweak the specification of components. For example, maybe we could change out the capacitors to have more capacitance, etc., to improve practicality and better meet the end user's needs.
These are some considerations that we have to take into account. After discussing our device with Dr. John Larocco, he mentioned that we may have to account for voltage from the heart and the resting voltage of neurons. To do this, we can use a magnetometer to measure the magnetic fields around the body. And since magnetic fields are perpendicular to current, we can measure the current to determine the electric signals from the heart. In the future, more research can be done to look into this issue. 3 potential areas of innovation are size, precision, and function. First, the device can be shrunk to fit into microfibers within the suit, allowing for maximum comfortability and practicality. Our initial design functions under limited costs and materials, but could be improved with more funding and time. With our current rudimentary sensors and equipment, it may not fit the accuracy needed to keep the semiconductors safe from ESD. With more accurate measurements and readers, a more precise voltage can be calculated. The functionality can be improved to also detect humidity, temperature, and other potential contaminants. Furthermore, the signal can be improved from a simple light to alarms and even vibrations.
And that concludes our presentation. Thank you for taking the time to review our device.